Hello everyone! In my previous video, I explained you how to derive a subspace system identification algorithm from scratch. And what you can see over here is the post I wrote that thoroughly explains the derivations. So I start from a Statespace model, and then at the end of the day I arrive at the data matrices and I explain you how to estimate the system matrices. Now, in this video, I will show you how to use this algorithm in practice. That is, I will explain you the Python codes that you can see over here. So we will use the Python codes to estimate a state space model of the system that you can see over here. This system consists of two masses that are connected by springs and dampers. If it displays a mass, for example m1, or if we apply a force F, a continuous force F, the system will oscillate. And the continuous time space state space model of the system is given by the equation 5. Now, the subspace identification algorithm will estimate a discrete time version of this system. Before I start, I have to mention that the links to this post and to the first part of this video are given in the description below this video. Okay, so let's start. So what you can see over here is the Spider Python environment that I'm using to test my codes. So why I like this environment? Because it reminds me of MATLAB. It's very easy to use. For example, if you want to execute these 5 lines of code, you can simply select them and you can execute them. And that's the advantage of the Spider Python environment. You don't need to execute a complete code, you can just execute certain code blocks. Okay, so the first step is to clear the workspace. You can type reset to clear the workspace and you can click on yes. Now the workspace is completely cleared. The next step is, of course, to import the important libraries. So we're going to import the NumPy library that's being used for matrix computation, for linear algebra operations, etc. Then we are going to introduce, that is to basically import the plotting library, and then we are going to import the inverse function from the NumPy linear algebra module, right? Then I'm going to import these 5 functions that you can see over here. These functions are the functions that I define, and these functions are given in this file. Here are the functions. And before I start, I have to mention that all the codes are given on my GitHub page, and of course a link to my GitHub page is provided in the description below. Okay, so let us import these libraries. I select them and I click on Run Cell. Perfect. Now, the next step is, of course, to define the model. So let us define our mass spring system. I select M1, M2, K1, K2, D1, and D2. K1 and K2 are the spring constant, and D1 and D2 are the damping constant. And you can see basically how the model looks like. It looks like this. This is basically the sketch of our system, and this is our state space model. Okay, now the next step is, of course, to define these matrices A, C, B, C, and C. How to do that? Well, it's very simple. We can use this NumPy function np.matrix, and we can define the matrix AC. AC stands for a continuous time domain, by simply using this notation. So this is the first row, this is the second row, this is the third row, etc. So we define subvectors that are separated by comma, and we define the matrix row-wise. So you can clearly see, for example, the second row of the matrix AC is given over here, and it should match this state space description. Okay, in the similar manner, we define the BC and CC matrices. You can see them over here. BC and CC, or C matrix, right? Let us execute these lines of code. And let's see what happens over here. We can type whos to see what is in our workspace. Perfect. We have these matrices. If you want to see the shape, you can simply type ac.shape, and you can basically get the shape of the matrix, its dimensions. Perfect. Okay, the next step is to define some parameters. The system has one input and output. I just defined these parameters over here, and the first step, of course, is to simulate this system in order to generate the data for identification. So I'm choosing the total number of time samples. These are the discrete time samples. So I'm using 300 samples, and here I choose the discretization constant. Now what I'm going to do, I'm just going to quickly jump into another code that shows that separately shows the discretization procedure, and it basically plots the data. So I'm going to use the same parameters. Let me just make sure that the matrices are correct and that basically the parameters are selected in the same way. So I'm just going to copy and paste these lines of codes here in order to obtain the same results, and let us simulate the system. So I'm choosing the time sample of 300 data samples, the sampling constant of 0.05 seconds, and I'm defining the input sequence. So the input sequence in this particular case is going to be, for example, a step function. So I want to see how my system behaves when I enter a step function to one of its inputs, that is, when this force over here is equal to a step signal. Now, the next step is to discretize the system. So I'm using the Beckford-Euler discretization method to go from continuous time domain to discrete time domain. So what is the main idea of the Beckford-Euler discretization method? Well, I approximate the first derivative over here by backward differences. Why backward differences are important? Well, backward differences result in a relatively stable model and relatively accurate model. That is, your discrete time system will be stable and it's going to accurately represent the continuous time dynamics. So basically, by applying these backward differences and by manipulating equations, you're going to obtain a discrete time version of the continuous time system, where this matrix A is going to be defined like this and B is going to be defined like this. So let us see how this works in a code. Here I perform the discretization. Since I have imported the important functions, the inverse function, I can simply use it, and let us discretize this. Notice that I'm now execute another piece of code just for illustration purposes. I'm going to go back to my original system identification code. And the next step, of course, is to check the eigenvalues. We want to make sure that the eigenvalues of the continuous time system are in the left side of the complex plane. That is, we want to make sure that the system is stable. Or better to say, its equilibrium point is asymptotically stable. I should say the system is asymptotically stable. Okay, now we can simply compute the basically eigenvalues by calling this function linear algebra from the NumPy library, and we can see the eigenvalues by simply copy and pasting this line of code over here. Let's see the eigenvalues. Okay, so we can see that the real parts are negative, meaning that the equilibrium point of the system is asymptotically stable. Now, the next step is to verify the eigenvalues of the discrete time system. Here we have computed the discrete time system matrix A, and we want to make sure that this matrix is also stable. Now, in discrete time, stability looks a little bit different. In discrete time case, the eigenvalues should be inside of the unit circle in order to achieve asymptotic stability. So after executing this line of code, we can basically obtain our discrete time eigenvalues, and I will not do it over here, but you can convince yourself by computing the magnitude of these complex numbers. You can basically convince yourself that all the eigenvalues are inside of the unit circle. Now, let us basically simulate the system. So how do we simulate the discrete time system? Well, it's very easy. Discretization is straightforward, and simulation, of course, is straightforward. Well, we are simply going to propagate the equation. So if this is our discrete time dynamics, by choosing an initial state, let's say x0, and having a sequence of control inputs, we can simply forward propagate this equation to simulate this system. So choose x0, and then you have x1 is ax0 plus bu0. Now that you have x1, you can recursively compute the x2 by simply writing ax1 plus bu1. And you can go forward until the end of our time window. We have time samples as the time window. So how to implement this in Python? It's super easy. I'm going to just define a for loop, define the initial condition, simulate the system response for this initial condition, and return the state sequence and return the output sequence. Okay, so let us see how the simulation works in practice. So what I'm going to do, I'm just going to simply memorize this function, to evaluate this function in Python memory, such that when I call the function, Python will know that it's already in its memory. So after memorizing the function, I can simply execute this line of code, and you can basically see the state sequence. You can do, for example, state dot shape, and it should be a matrix, right? 4 rows and 301 columns, since we have 4 states and we have actually 301 samples, since the first column corresponds to initial condition. And you can simply plot the output to see the output shape. So this is the output of the system when you apply a step signal, and this is quite reasonable since the system is damped. Okay, so let us go back to our code. I'm just going to reset the workspace once more to erase everything, and I remember that I stopped over here, so I'm going to again execute until here. Now, here's the discretization that I explained previously. I'm just going to execute these lines of codes. These are the eigenvalues. Here, for simplicity and for completeness of this presentation, I'm just repeating these lines of code, right? So now we basically have the discrete time system, and we have checked the eigenvalues. The eigenvalues should be fine. Again, you can convince yourself by evaluating these 2 lines of code. Okay, so the next step is to define the input for the system identification. Previously, I have used the step input to simulate the system. However, this is done just for illustration purposes, since I want to convince you that the system performs, or it's kind of behaves how we expected it to behave, right? It's a basically damped system. When you apply a step signal, it should kind of follow that step signal with some attenuation, right? And the next step is, of course, to use more realistic input and to use something that can be used for system identification. So what I'm going to do, I'm going to define a random input signal that's going to be used for system identification. Why I'm using the random signal? Well, the random signal will most likely excite all the modes in the system, meaning that our outputs will contain enough information such that we can estimate such a system. There is something called persistency of excitation condition in the system identification literature. This persistency of excitation condition is a necessary condition for consistently estimating the system dynamics. And this random signal, or white noise random signal, or pseudo-random noise signal, or some kind of randomly constructed signal will most likely satisfy the persistent C of excitation signal. Okay, so I'm defining the input signal, and here it is. Its entries are drawn from a uniform distribution on the interval from 0 to 1, and you can see the entries over here, and I'm also defining a random initial condition for simulating the system dynamics. This initial condition, of course, in the case of real life system is usually not known, since you're only going to collect the output data from the system, and the initial state is only in some specific situations when you know that basically the system starts from rest, is usually known. Okay. And we need an additional data set. Besides the data set used for system identification, we need an additional data set that's used for model validation. Right. So what I'm going to do, I'm going to define another input and another initial state that are statistically independent from the input and the initial states that are used for system identification. Now, this validation data set will be used to validate the performance of the estimated model. What does it mean to validate the performance? I can use this data set, the identification data set, to estimate the system model. And I can kind of evaluate the performance of the estimated model on the data set that's being used for system identification. How I can do that? Well, I can simply simulate the estimated model, and I can basically compare the simulation results of the estimated model with the data sets that are being used for system identification. And usually this will provide a very good match. Since the data is being used for system identification, the model will somehow be based on such a data. This is not a good procedure. A more realistic and a more statistically justified procedure is to generate another data set that's not being used for system identification, and to simulate the system and to compare the simulation response with the validation data set. And by comparing, for example, the output of the validation data set with the output of the simulated estimated system, we can get a much better insight into the performance of our estimated model. So that's why I'm defining another data set. Then the next step is naturally just to simulate the system. I'm going to simulate the system in order to obtain the identification data, and I'm going to simulate our true system to obtain the validation data. Okay. Now, the first step in the subspace identification method is to estimate the matrix of Markov parameters. So here you can see the matrix of the Markov parameters, and the equation 19 is a fundamental equation for us. Now, if you have watched my previous video or the first part of this video, you could basically get some intuition about this equation 19. This equation 19 tells us that the system output at the time instant k can be represented as a linear combination of past inputs and past outputs, and plus, of course, the noise term over here. So let us see this equation. So this equation is basically telling us that the system output at the time instant k is a linear combination of something that looks like this: m1u times uk minus 1 plus m2u uk minus 2 plus until mp u uk minus p plus the part corresponding to system outputs u, actually here we have now y, be careful, k minus 1 plus m2 y k minus 2 until mp y yk minus p, and of course we have the noise term. These matrices over here are the system Markov parameters. And the first step is to estimate them. How do we do that? Well, if you see this equation, these terms are known, since we know the input, and the assumption is that we have collected the data, that is the output of the system, and then we can use these outputs also as known variables in this equation. And on the basis of this equation, we can simply form a multivariable least squares problem, and we can estimate these matrices. So how do we do that in Python? It's very easy. It's very easy. We have stopped over here, right? What do? We basically define Hankel matrices. We just basically live the system in the discrete time domain. We form the matrices and we just apply the pseudo inverse, and all the steps are given over here. We basically solve this least squares problem. Starting from this equation, we kind of stack all the outputs next to each other. We stack all the past inputs and outputs. Then we know this equation. This is the noise term that we don't know, so we basically minimize the difference between the left side and the right side. The left side is known, the right side is known, and then we obtain an estimate of the system Markov parameters. And this is the Python code for doing that. So I have defined the function, performed all the basic steps. Here is our pseudo inverse. I'm calling the linear algebra dot pseudo inverse to compute the pseudo inverse. The next step is, of course, to estimate the system matrices. And in order to estimate the system matrices, we basically need to use the estimated Markov parameters. So what do? We use the estimated Markov parameters to form this equation that you can see over here, right? So we go basically, this is the first basically r rows of the system Markov parameters, or the complete Markov parameters matrix. We form the first row, the second row, etc., etc. We form this matrix. Then on basis of this equation 28, we conclude that basically by computing the row space of the right hand side, we can estimate the state sequence. By estimating the state sequence, we can basically estimate the system matrices. So here is how we estimate the state sequence. We basically perform a singular value decomposition, and on the basis of such a singular value decomposition, we can form the state sequence or the state sequence matrix. And once we have the state sequence matrix, we can again use a simple least squares method to estimate A, B, and C system matrices. Here are all the details. They're provided in the previous video. Now, to estimate the state sequence, we need to have a guess of the model order. Since we don't know a priori the model order, right? This is something unknown. We only know the output of the system. So here you need to guess the value. So let us, for example, guess the value of 2. Okay, so let us execute these two functions. The first function is going to basically estimate the Markov parameters. I explained this function. And the second function is going to estimate the state sequence and to return you basically the system matrices. So here is the function that estimates the model. You first estimate the state sequence by performing a singular value decomposition. You can see it over here. Then you construct certain Hankel matrices and you estimate the state sequence that you can see over here, and you return the results. I'm not going to go over this function since it's going to take me basically half an hour to explain you all the steps, but the steps are very trivial. If you understand this part, if you understand the code, if you understand the derivation, it's very easy to derive the function. And the nice thing about subspace identification method is that we are using only basic numerical linear algebra steps plus singular value decomposition. And if we execute these two lines of codes, that is, we first estimate the Markov parameters, then we plug in the estimated Markov parameters in this function estimate the model, this function estimates the state sequence and estimates the system matrices. And we basically execute. Here we obtain the results. Now, I forgot to mention that for this first function you need to select the past value. This is the parameter p that's basically being used over here. Again, this is a value that you need to guess. And here I assume 10. There is a very nice and systematic procedure for finding this parameter. You can, for example, use a Kaike information criterion. I'm going to explain this in one of my next videos, maybe in future videos, where I'm going to talk about time series and validation of time series and model order choice for time series. And we use this very nice criterion called a Kaike information criterion to select this past value systematically. However, in this video, in this code, you can simply choose the value. Let's say you can choose 10. And let's see the results. So first, what I'm going to plot, I'm going to give you a singular values plot. So this plot basically shows the singular values of the matrix that you can see over here. So the product of the matrix formed on the basis of the estimated Markov parameters and this matrix over here that contains the input-output. So the singular values are very important since they can reveal the true model order. So let us analyze this plot. What can we observe over here? We can observe a huge gap between the fourth and fifth singular value. Don't be confused over here since the index starts from 0. That's the Python notation. This is basically first singular value, second, third, fourth, and fifth. So there is a huge gap. And basically by detecting the gap, we can reveal the true model order. And here the data tells us, okay, the model order is equal to 4. And this actually perfectly matches the model order of the true system, because you can see that the true system has 4 state space variables: x1, position of the first mass; x2, velocity of the first mass; x3, position of the second mass; and x4, velocity of the second mass. Now let us go back to our code. You can see over here that I assume the model order 2. I don't know exactly what is the model order 2 since I was not able to see this graph, right? So I assume 2. But basically assume the model order of 2, I'm collecting information corresponding to certain rows or columns of matrices in a singular value decomposition. So if you analyze our singular value decomposition over here, you can see that I'm basically taking first n hat rows of this matrix Vt in the this singular value decomposition. Vt I simply denoted the V transpose. So V with the lower with the subscript T corresponds to Vt. So I'm selecting the first n hat rows of this matrix. And by choosing the model order of 2, n hat becomes 2, so I'm choosing the first 2 rows of this matrix. And these 2 first rows are somehow weighted in the total information content like this. We can see that I need to take more rows. More rows are dominant, so I need to take 4 rows. And this is the meaning of the singular value decomposition. So singular value decomposition can reveal the model order. Of course, they are much more complicated and I would say much more statistically sound methods to estimate the model order. However, I'm not going to explain them in this video. If you want to know more about them, you can look into one of my papers that's posted on Archive. You can look into this paper over here. Okay, so let us see the performance for the model order of 2. Let us just leave the model order as it is. Later on we can increase it to 4 to see the difference, but let's just leave it as 2. Now that we have estimated the system model for the model order of 2, we want to evaluate its performance. So how to evaluate the system performance? Well, we are going to use the validation data set. We first are going to simulate the estimated model, and we are going to choose the output of the simulated estimated model. This output will be compared with the output from the validation data set. And remember that validation data set is obtained by simulating the true system. So we are going to take the output of the true system, which in reality is your physical system, and we are going to compare it with the output of the estimated model. However, to perform this comparison, we need to simulate the estimated model. However, to simulate the estimated model, we need to know the initial state. And this initial state should correspond to initial state of the true system for which the validation data set is obtained. However, we don't know this initial state, so we also need to estimate this initial state. You can also assume a 0 initial state, however, then you will have some errors in the transient response. So we want to eliminate these errors. So how to estimate the initial condition of the system? Well, we are going to use a simple open loop observer. Don't be scared by the word observer. Observer is nothing less than a state estimator. So here's how we estimate the initial state. This is our system, our estimated system. Here I'm going to neglect the measurement noise and disturbances. Now, on the basis of this equation, we can perform the so-called lifting procedure. So the lifting procedure is to lift the system output in the time domain. So if I group all the outputs in a vector, I want to see how my right-hand side will look like. How will the right-hand side of this equation look like? Well, not surprisingly, here we are going to have a matrix that looks like an observability matrix. And this matrix will multiply the initial state, and plus over here we will have another interesting matrix. And this matrix will consist of the system Markov parameters or the impulse response corresponding to inputs. This is H here and this is H. So this matrix here is going to have zeros. Here we are going to have C times B, 0, 0, zeros, etc. We are here going to have C, A, H minus 1. Again, this is not 10, this is H, B, and it's going to go until CB, and it's going to be 0 here. Notice that these elements on the subdiagonals are identical. If we call this term Y, we call this O, capital O, or calligraphic O, X0. We call this matrix, for example, L, and we call this vectors capital U. We are going to obtain this equation. Now, in this equation, this part is known. This part is known on the basis of our estimated model. This part is known, we can form since we have estimated the model. That is, we know A, B, and C, and this part is known. We can construct this part using certain part of validation data set. So we can take a short first, for example, 10-20 samples from the validation data set, that is H, for example, is like 30, and we can form this matrix equation, and from this equation we can estimate x0. We can simply form a least squares problem. We can say minimize with respect to x0 this difference y minus basically L u minus O x0. Since this part is known, this part is known, we can simply compute x0 as O transpose O inverse O transpose y minus L u. You can verify, you can check these equations if I made an error. However, these are the classical equations for the open loop observer, and this is the basic idea. You can also look into my post to verify these equations. So here's our code. What I'm doing over here, I'm choosing H equal to 10. I'm forming these equations and I'm estimating the initial state. Here's this function, you can look it up over here, estimate initial. Basically, you're performing a pseudo inverse. These are the matrices, and it's very simple. So I'm going to estimate the initial state. Now we have the initial state. Let's look into the initial state. You can compare this initial state with the state used to simulate and to obtain the validation data set. And what I'm going to do now, I'm going to simulate the estimated model starting from the estimated initial state and using the estimated system matrices to obtain the predictions of the validation data set. So here they are, and then I'm going to compute the relative error. So I'm going to compute the relative error between the validation output and the simulated output of the system on the basis of the estimated initial state to see what is the error. So I'm obtaining a relative error of 36 and the variance accounted for of 86. This measure variance accounted for, I wrote the functions that kind of compute this value, and you can look it up. It's called, the function is called model error, and you can see how these variances accounted for are computed. They're one of the measures of this model quality. If the variance accounted for is 100, then basically your model is a perfect model. If it's 0, then your model is really not good. So once I have compared the outputs, I see 36% relative error. That's kind of a significant relative error. I can basically plot the results, and what I can see over here, I can see the real output. This is basically the validation data set output obtained by simulating the true system, and the red line is the prediction. So the match is not very good. Okay, so let's see what happens if we improve the model. Let's improve the model. We can improve the model by increasing the model order. Let's increase the model order to 3, and let's see what happens. Let's see the results over here. Let's see the match. Okay, seems that the results are kind of better, right? We have a variance accounted for of 50, actually the 72%, so the variance is better. However, the relative error is not good. Okay, and the final step is basically to increase the model order for 1, and this should be the model order according to our singular value decomposition. So you can basically guess any model order, compute the singular values, and then you can look into the gap of singular values and find the dominant gap, and the singular value before the significant drop should be a relatively good model order. And let's see the results over here. Let's see what happens. And we see that basically the relative error is 0, effectively 0, and the variance accounted for is 100%. And we can see that real output perfectly matches the predicted output. or the predicted output perfectly matches the real system output. And the subspace method works very well. Okay, that would be all for today. I hope that you like this video. If you like this video, please support this channel, click on like or subscribe.